There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium.
Man, I studied so hard for that thermodynamics test. I think my teacher hates me.
I'm your teacher.
Oh, well, that last test was mean.
It wasn't that bad. What did you miss?
I think I had the most trouble with isobaric.
Isobaric simply means a process that takes place at constant pressure.
Oh, I see. In that case, I have an isobar in my head. I think your test is responsible.
The process of calculating anything for constant pressure is really rather simple. For work, you simply take the change in volume multiplied by the pressure.
Oh, what about a change in internal energy?
A change in internal energy is equal to the change in heat capacity with respect to volume integrated from the initial temperature to the final temperature. The same equation also applies to enthalpy by simply replacing the C sub V with C sub P.
I see. I have another important question.
What is that?
Why are you British and why are we in a courtroom?
Well, I'm not sure.
Well, I'm leaving now. Have a great day eating tea and drinking crumpets or whatever it is British people do.
I wonder how he figured out I hate him. I'll have to be more careful next year.
Welcome to our program. We have an exciting program for you tonight. We'll be hearing from two renowned thermodynamics experts to talk to us about ideal gas behavior under isochoric and isothermal conditions.
Hello, I'm sound volume.
And I'm Constance temperature.
Say, Constance, do you know what the difference between you and I is?
Why do I get the feeling you're teeing up for a really poor joke? I don't know, Sam. What is it?
I don't do any work.
I was right as usual. Why don't you explain that corny joke to the audience?
You see, work is defined as the change in volume integrated over the change in pressure. In other words, you can only get a change in work if you have a change in volume. So for a constant volume process, no work is done. Oh, come on, that was funny. You're just jealous because you have no internal energy.
Well, that is true. For an isothermal process, internal energy and enthalpy are equal to 0. Q is equal to R times T times the natural log of volume 2 divided by volume 1.
But that's not the whole story.
That's true. You can also find Q in terms of pressure. If you take negative R times T times the natural log of pressure 2 divided by pressure 1, you also get Q. What about you, Sam? You only explained work with that corny joke.
Okay, fine. For me, Q is equal to the integral of C sub V with respect to temperature.
And your change in enthalpy and internal energy?
Well, since internal energy equals work plus Q, my internal energy is just equal to Q. As for my enthalpy, it's just equal to C sub P integrated with respect to temperature. You didn't say anything about your work.
That's because my work is equal to the negative of my Q.
Thank you, Constance and Sam. In other news, scientists make for lousy banter. After the break, we have the latest news on the epidemic of exploding kittens. Is your cat at risk? Find out after this word from our sponsors, makers of the exploding kitten vaccine.
Hey, Newton, Any new ideas hit you lately?
You know that's relative, Albert.
You know what? For some random reason, I feel like talking about adiabatic behavior of an ideal gas.
What a fantastically convenient plot device. What specifically would you like to talk about?
Well, as the father of physics and calculus, I'm sure you're familiar with the fact that adiabatic behavior of a gas implies that the differential change in Q is equal to zero.
Sounds good to me. Under such conditions, how would you perform calculations for factors such as enthalpy, work, and internal energy?
Well, Sir Newton, I'd be happy to explain it. For most of the calculations, we define something called gamma.
And how exactly is gamma defined?
Gamma is defined as the heat capacity with respect to pressure divided by the heat capacity with respect to volume.
That's fantastic, but how is that useful?
Using gamma, you can calculate all sorts of things. For instance, 2 volumes and 1 temperature or 2 temperatures and 1 volume, you can figure out the missing term using this handy equation. T2 divided by T1 is equal to volume 1 divided by volume 2 to the ideal gas constant divided by the heat capacity with respect to volume power.
I am Sir Isaac Newton, I can read.
My apologies. Sometimes, I just get the impression someone is watching us, and I feel like I should do a good job explaining things, but onto an equation where you actually use gamma. For example, if you wish to calculate work, you can use gamma like this. Work is equal to...
As I said, I can read.
I know, but I still get the feeling we were being watched. The change in enthalpy for an adiabatic process is the integral of the heat capacity with respect to pressure with respect to temperature. You see an integral.
I was a key part of the development of calculus. I know what an integral is.
Sorry, I always assumed it was Gottfried Leibniz who invented calculus. At any rate, since Q equals 0, work is equal to the change in internal energy.
And what is that equal to?
Well, there are lots of ways to find internal energy and work. You can either integrate heat capacity at constant volume with respect to temperature, or by multiplying the change in temperature by the ideal gas constant and dividing by gamma minus 1.
I see. That's very interesting.
I am Queen Elizabeth.
Well, that was strange.
She just walked through the wall. I'm not sure how that's possible.
If we start questioning the plausibility of this, everything falls apart.
Fair enough.
This was a triumph. I'm making a note here, huge success. It's hard to overstate my satisfaction. Aperture science. We do what we must because